So before I go over the integration by parts examples, I'd just like to cover the Liot rule, where L stands for ln, I stands for inverse trig, A is algebraic, and that means like polynomials that have x in them, like these examples, and then T and E are just trig and exponential. So inverse trig just means like arctan, arcsine, etc., etc. And the reason why you want to know this is because as you go to the right, it gets easier to integrate the function, but as you go towards the left, you would want to find the derivative instead. So for example, like if you go to the right and you have something like a trig function, you can easily integrate that. Like, let's, for example, look at sine x, the integral of that. That's just going to be negative cos x. And something like the integral of e to the x, so that's just e to the x plus c. But something like the integral of ln x, well, that's kind of complicated, and we can't exactly integrate that by inspection. So we would set up our u, our du, dv, and v, and we would put in u ln x, and we can easily just differentiate that as 1 over x, and then the dv, well, if you look at the integral ln x dx, all that's left is dx, and the v would just then be x. And then we can just plug it into our integration by parts formula. Now let's look at the integral x ln x dx. If you remember from the Liot rule, we always pick ln x as the u if it's available in the integral, so let's do that, and we differentiate that, we get 1 over x, and then we're left with dv as x, and x dx actually, and v will just be x squared over 2 if we integrate the dv. And then we can just plug it into our integration by parts formula, which is the u dv equals uv minus v du, and that's actually going to just be ln x times x squared over 2 minus, this should be the integral actually, these should be the integral, times x squared over 2 times 1 over x, and then you can get some cancellation happening in the integral. So you're just going to have, you're going to be left with x over 2, and x over 2 is just going to be just an algebraic integral, and you can just use the power rule to solve that. It's just going to be x squared over 4. So you can combine that together, and you can rewrite it if you want at the end. So you're left with that. Again, a similar sort of example, this time with ln x cubed. So let's let u equal to ln x cubed, and dv is just dx in this case, and then if we differentiate ln x cubed, it's just going to be 1 over x cubed times the derivative of x cubed, which is 3 times x squared, and v is just going to be x. Then plug it back into the IBP formula. It's going to be ln x times v, which is x, minus v du, so x times 1 over x cubed times 3x squared, and then you get a lot of cancellation going on, so you end up having just 3 left over in the integral, and that's just going to give you 3x to add to it. Next, we're going to look at x squared times e to the 3x. Now, if you remember from the Liot rule, exponentials after algebraic, so we're going to let u equal to the algebraic term, and if we differentiate that, it's going to be 2x dx, and the dv is just e to the 3x, and if we integrate that, it's going to be e to the 3x over 3, and then we put it into the IBP formula, so it's going to be v times u, which is x squared times e to the 3x over 3, minus v du, so it's going to be e to the 3x over 3 times 2x, and we're going to have to do IBP again here. So here we get another algebraic term times an exponential, so let's just work with that integral. Let's take the minus 1/3 out, so we're just left with e to the 3x times 2x dx. Actually, let's take out the 2 as well. So now we can just let let's let a equal to the algebraic part, and if you differentiate that, it's just going to give you dx, and then db is just going to be e to the 3x, and then once again b is just going to be e to the 3x over 3. So then you use the integration by parts formula again to get a times b, which is x times e to the 3x over 3 minus b times dA, and then you just get e to the 3x over 3 in the integral, and you can do this by inspection. It's just going to be e to the 3x over 3, and then we can simplify it a little bit more, so it's just going to be e to the 3x over 3 minus 1 over 9 e to the 3x plus c, and then we can just plug this back into the integral we were trying to solve, so that our final integral, our final answer just becomes x squared times e to the 3x over 3 minus 2/3, and the integral that we solved here, so it's just going to be e to the 3x times 3, actually let me erase that integral, we don't need it, minus 1 over 9 e to the 3x, I'm just writing what we circled there, and then we can just expand that to get the final answer. Now let's look at arctan 3x dx. So from the Liat rule, arctan is inverse trig, and so we can just let u equal to arctan, and then if we differentiate that, we just get 1 over 1 plus 3x squared times the derivative of 3x, which is 3, and then the dv is just dx, so the v is going to be x, and then we use the IBP formula, so we get u times v, which is arctan 3x times x minus v du, which is x times 3 over 1 plus 9x squared, if you expand the 3x squared there. And you end up getting, inside the integral, you get 3x over 1 plus 9x squared. And if you remember, you can do this by inspection, but for the sake of making it more clear, I'm going to use substitution. So I'm going to substitute in 9x squared plus 1, and if we differentiate that, that's just 18x, so we can represent this as 3x by dividing it by 6, so you end up getting, you can represent the original integral as 1 over u times du over 6, and you can integrate that pretty easily. It's just ln absolute value of u over 6 plus c, and put the u back in, it's just ln 9x squared plus 1 over 6, and then you can just fill in the original integral. Now let's look at an arctan example with an x in it. So again, inverse trig comes before algebraic, so we can just let u equal to arctan and differentiate that, and then dv equals to x, and if we integrate that, that's going to be x squared over 2. And then we can plug those values into the IBP formula, so it's going to be arctan x times x squared over 2 minus v du, so x squared over 2 times 1 plus x squared, yes. So now if we deal with this integral, we can just look at we can take out the negative half out, so we're left with x squared over 1 plus x squared, and here what you can do, you can actually use this technique where you split up the numerator into x squared plus 1 minus 1, and this is a technique that's really handy. You'll see this quite often being used. So then you can just group the numerator terms together with the denominator terms, so you get something like that. And it's a lot quicker to do than using partial fraction decomposition. So you can end up splitting the integral then. So you're just left with basically 1 as one of the integrals, and the other one is just 1 over 1 plus x squared, and you know that that's arctan x, the integral, and that's just 1, so it's going to be x, so that this integral is just going to be x minus arctan x, so you can plug that back into the original integral, arctan x times x squared over 2 minus half times this, so it's going to be x minus arctan x. for this example, I'm going to write it as x times 1 over cos squared x, because 1 over cos squared x is just secant squared x, so we can just write like that. And if you remember from previous videos, secant squared x is just the derivative of tangent. So what we can do is we can actually let that equal our dv, so that u equals x, and differentiate that as just dx, and dv equals secant squared x, so v is equal to tangent x. And then use the IBP formula, and you will get tan x times x minus v times du, so just tan x. And if you remember from previous antiderivative inspection video, the integral of tan x is just ln of secant x, or you can write it as minus ln cos x if you want. They're the same thing. Whichever one you write should be fine. So for this example, I'm going to rewrite it as sine x times e to the negative x dx. And here, if you remember the Liat rule, if I write it in the colors, the trig and exponential were written in the same colors, which means it doesn't really matter which one you choose for u or dv. So we can choose either sine x or e to the negative x if you want. So let's go ahead and choose sine x for our u. And if we differentiate that, that's just cos x, and dv e to the negative x, integrate that, that's going to be negative e to the negative x. And plug it into our IBP formula. It's going to be sine x times e to the negative x minus v du, so negative e to the x times cos x dx. And you see we have another integral that where we have a trigonometric times an exponential, so we're going to have to do IBP again on this part. An important note, since we use the trig function as our u in this substitution, we have to use the trig function again. So since we use sine x, we have to use cos x again. If we use exponential, we would have to use exponential again. So just let the new u equal to cos x, and then differentiate that, that's just negative sine. And the du is e to the negative x, so again it's going to be negative e to the negative x, and then plug that back into our integration by parts formula. It's going to be cos x times e to the negative x minus v times du, so negative e to the negative x times negative sine. The negatives become a positive, and you notice that we reacquire our original integral, which was u dv. So we can let our original integral equal to some variable like I, and rewrite our original integral as I equals what we wrote before, so negatives here, I'm just copying down what we wrote before, and the integral that we just got, so it's going to be cos x times e to the negative x, and this is just I here, so we can then move the i's to the other side, so we're left with sine x times e to the negative x, and I'm going to factor out the negative. In fact, I'm going to factor out the e to the negative x as well. So then in the next step we can just get our answer by dividing both sides by 2. This example is similar to the next one in terms of what we have to do, so let's first split it up into secant x times secant squared x, and we've already seen secant squared x, that's just the derivative of tangent x. So again, let's let u equal to secant x, and du equal to secant x times tan x, that's the derivative of secant x if you recall, and again dv equal to secant squared means that v is equal to tan. And then let's plug it into our integration by parts formula. So it's going to be u times v minus integral of v times u du. And here, what we can do is we can actually represent tan squared x as secant squared x minus 1, which is a trig identity. If you remember, tan squared x plus 1 is equal to secant squared x. So that's why we can do that. So then the integral that we are trying to solve becomes secant squared x minus 1 times secant x. And then you can expand that out, so you get secant cubed x minus secant x, and you notice secant cubed x is what we're looking for. So we can do a similar sort of trick to what we did before. We can let some variable, okay, some I equals to secant cubed x integral, and then we can let I equal to what we're trying to find. So it's just going to be secant x tan x minus, so I minus secant x dx integral. And if you remember from the integrating by inspection, the integral of secant x is just ln secant x plus tan x. Yes, I believe that's correct. And then we can just do the same thing. We can divide the right hand side by 2. So the last example I'm going to do is this one, the integral of x to the 5 cos x cubed. Now this is an IBP question, but before we do the actual integration by parts, we have to do a u sub. So we're going to let u equal to x cubed, and if we differentiate that, we just get 3x squared. And then du over 3 equals to x squared. So now we have a way of representing x squared and x cubed. So the x to the 5, we can represent that as x squared times x cubed, right? So we can just let the original integral equal to u cos u times du over 3. And now we can use integration by parts. We can just let our new u equal to u, and our dv equal to cos u. So let's do that. Let's let u equal to u, du equal to du, and then dv is equal to cos u. And then if you integrate that, that's just going to be sine u. And then use the formula, so it's going to be u times sine u minus v times du, so that's just sine u du, and then the integral of sine u is just negative cos u, so that just becomes positive cos u, and then we can just plug back in the u, which was x cubed, and then we get our final answer. So I know that this video was pretty long. Thank you very much for sticking around until the end, and I hope this helped.